Kia ora. I hope you guys are having a good lockdown. This is the second lesson or task, whatever you want to call it, for our week 5 for level 3 chemistry. So lesson number 1 or task number 1, whatever you want to call it, you should have done your electrolysis quiz. Remember that was a Google Doc. Each student should have their own document, and you can just write in it, or you can take a photo of your work if you prefer to draw the diagram and annotate that, and then put that onto the quiz image. So this second lesson then is going to be focusing on the galvanic cell, and basically looking at how that galvanic cell is able to produce energy. We're going to focus a lot on the diagram and basically the key features of that diagram and why those different key features are there. But before we do that, you need to do your mahia, which is just a quick drawing of the electrolytic cell and just stating 2 key features of it. And the reason why I want you to do that is because you're going to be able to then see the difference when we start talking about this galvanic cell. Remember that this compare and contrast is really important if you want to get that excellence, because that's the final part of this internal. If you are in my class, can you please make sure that you also do that weekly reflection for last week, aka week number 4. It's really good then for you guys to do that so you can tie the various weeks of material together, and it's a nice little check-in that you can do with me. So take a moment right now and pause the video so you can do your mahia. Cool. All right, let me go over the answer to that. I also want to note that if you have the booklet with you, we are actually still on lesson number 7. There hasn't been too many changes when it comes to, there has been no changes to the content. I just have done slight changes in the lesson teaching just because it is now remote learning. Anyway, let's look at the answer. So what I wanted you guys to do for this was just do a quick electrolytic cell and factor in the kind of the key points to it. The first kind of key point that you should have is that there's only one beaker. The other thing that you can be noting with that is that both electrodes are obviously in that one beaker, and when those electrodes are connected, we need to have a power supply. I'm trying to think what else you might want to note in there. Obviously, with this, it is either in the, you have an ionic compound, which is either in the molten or aqueous state. Trying to think what else. Let's see. Oh, we should be labeling our cathode and anode. Let's say this one's the cathode. This one's the anode. Anode has your oxidation. Cathode has your reduction. When it comes to positive and negative, the cathode will be negative and the anode would be positive. Electrons are going in this direction. I think that was mainly it when it comes to that. Cathode, we should see a metal sheet forming or some sort of shininess forming. Not always the case, but general pattern that you see kind of metal forming. Whereas on the anode, you generally see bubbles. And the key thing to remember about this reaction when we're talking about electrolysis is that we are generally, for the most part, depending on what we're given, but generally speaking, you should be going from your ions to your elements. So remember, in this case, we are talking about electrolysis. And this is an important reminder because when we look at the galvanic cells, there's some real key things that are very, very different from it. Anyway, I will make sure that gets scanned so you guys have a copy of that. But if you want to pause, you can if you want to copy anything down. All right, cool. So let's move on to the remainder of today's lesson. So here's our remote learning lesson plan for today. The first thing I have is to consider the following question. I then have you guys do a describe then explain, which I think hopefully those that were in my class remember doing this for the electrolytic cell. It's just really good for you guys just to make some observations before I go into the specifics to see what you guys can pull. Then we will watch a video on the galvanic cell. I will talk about the general galvanic cell setup, and I'll also give you guys a worked example. And then lastly, I will give you a list of things that you guys can do as follow-up work. There's lots of different choices. I do not expect you to do all of them. It's just a matter of allowing it to be differentiated based on where you are with your online learning, and just to give you, like I said, a variety of choices or extra stuff if you feel like you need that practice. Feel free to pause this video at any point because I know it is going to be more teacher focused and you might need a break, and that's totally fine if you feel like you need to do that. On our checklist today, we are taking off a lot of things when it comes to it. Basically, we're looking at things that are related to the galvanic cell, so like 12 and 13. 15 is just talking again about what you would expect for the characteristics specifically, but you should have seen these words like cathode and anode before. Salt bridge will be new. And then lastly, if you can identify the oxidant and reductant using the standard reduction potential, that's basically our resource sheet, which you have started to kind of get an idea on. All right, so I have a consider the following question. We know when we put magnesium into acid, there's going to be a transfer of electrons. I can obviously see a reaction occurring because my magnesium is turning to the ion. I no longer can see it as the magnesium metal, and I see bubbles forming, which when we do a pop test, we can confirm it's hydrogen gas. So obviously there's electrons moving around and being transferred, and my question to you is, from that reaction alone, why can't we use it for electricity? So take a moment to pause and think about that. All right, so the reason why is because even though we have these electrons moving, we're not actually controlling that flow of electrons. So it's really important that we can basically force them to go in a certain direction, and when we can force them to go in this direction, in this pathway, we can then use that to generate electricity. So the galvanic cell that we talk about is actually going to be the way that we can explain how we've manipulated this redox equation to force the electrons to go in a specific direction. All right, so here's another activity that's for you guys. So what you can see here is a little GIF of a galvanic cell. You can basically see what happens when we connect the circuit using that salt bridge. So take a moment to watch it. I want you guys to write down the observations that you notice. So you can already make some observations on what galvanic cells are. For example, just thinking about the mahia and the fact that I drew one beaker, whereas in this case there's clearly two beakers. So I want you guys to make observations like that, and if you want to give it a go and try to explain why maybe we have this sort of setup. So I'm just going to stop talking for a little while so that way you can watch the GIF a few times, and then I would suggest you pause the video, write down your observations, and then see if you can explain them. All right, I'm hoping by seeing it twice you have some ideas of what's happening. So I would say pause the video at this point so you can quickly jot down some of the things that you are seeing. Cool. So let's start explaining what we are seeing and why we see those sort of things. The first thing when we're thinking about with this galvanic cell is that I want electricity, and for me to do that, I need to isolate the electron transfer. I need to control that electron transfer. I need to force it to basically go a direction that I want it to go in. And the key then to make sure that we control this movement is by basically separating the two half reactions. So I'm trying to separate the redox reaction. I'm trying to separate one half into the oxidation half and the other half into the reduction half. Now, these two half reactions are still connected, and they are connected through the electrodes, the wire, the electrodes which are connected by a wire, and then also something known as a salt bridge. And you guys will be able to kind of see the importance of that. But before I go into the general the general galvanic cell setup, I want to play for you guys a video so you can actually see in real time that this works.
Experiment 12. Electrochemistry. Voltaic cells. Chemicals and apparatus. Copper sulfate and zinc sulfate at different concentrations. Multimeter, copper and zinc strips and wires. Salt bridge. Put 50 milliliters of copper sulfate and zinc sulfate in different beakers. Zinc electrode is connected with black wire, and it is connected to the black side of multimeter. Copper electrode is connected with red wire, and it is connected to the red side of multimeter, which is voltmeter input. To measure the voltage, DCV 2000 condition is used in multimeter. Salt bridge, including solution of potassium sulfate salt, is dipped into the solution. Copper electrode is dipped into the copper sulfate solution, while zinc electrode is dipped into the zinc sulfate solution. Voltage is observed by multimeter. Record the voltage after dividing it by 1000. The same procedure is applied to different solutions. Vmax and E0 cell will be calculated from the data.
Cool. So I hope that video has helped you kind of see that it does actually work and it does generate electricity. So let's go on to talking about the general setup for my galvanic cells. Cool. So the first thing I want us to note when we are looking at this, and this is generally, I want to note it because I know when you guys are writing your electrolytic cells, the first thing you write down is that it is a non-spontaneous reaction, and we can see that because of that DC power connection. In this case, I have drawn a voltmeter. So what that voltmeter there is trying to indicate is that we are having a spontaneous reaction that is producing voltage. You don't need to draw the voltmeter there. It's just I have drawn it there to help you remember that this is a spontaneous reaction. So I'll write that as my first point for you guys to think about. We have that voltmeter there. This generates electricity. So no need to hook it up to a power supply. If you guys remember, I talked about the E-cell calculation that we're going to be learning about. Looking at my lesson plan, that won't be until next week. But just so you guys remember, or that you guys note, the E-cell in this case, when we calculate it, will be a positive number. Just FYI when we are justifying what's going on. All right, cool. The other thing that we need to note as kind of general patterns that you will notice as kind of like key standout features is that you will notice that there are two beakers here, whereas with the electrolytic cell, there's only one beaker. And the reason why we want these two beakers is so that way we can separate the redox reaction. And by separating that redox reaction, what I'm going to then be able to do is basically control that flow of electrons. Cool. All right. Some other things that you might have noticed that are a little bit different in this case. The first, or not different, similar. In this case, one of the things that you will see that is similar is the fact that I have drawn little squiggly lines here, like that. Those squiggly lines are just to represent the fact that we have ionic solutions, and these ionic solutions are going to be aqueous in this case. Now, the thing to note about these ionic solutions is that they will be different. And you'll see in that specific example that I give why that difference is important. Some other things to kind of note as things. The other cathode and anode are still going to be paired to the same oxidation and reduction reaction. So the cathode will have the reduction. The anode will have the oxidation. So that doesn't change. However, what does change is the symbol. So a cathode will be positive in a galvanic cell, and the anode will be negative in the galvanic cell. So do keep in mind that that is different. The other thing to kind of note are the electrodes. The electrodes, basically you have two choices with those. So these electrodes will often be made up of different metals, or they'll both be innate. Or it will be, say for example, a metal with an what we call inert electrode. So inert electrode would be basically like your carbon electrode, or unreactive metal, which would be platinum. Or they could be both inert. It really depends on the reaction. So just kind of keep that in mind with the electrode when you're looking at it. The other thing to note about these electrodes is that often if they are metal, it'll be the ion pair. So what I mean by the metal with the iron pair, let's say that this is it'll be like a copper sulfate and a copper electrode, if that makes sense. Again, like I said, I'm going to show you guys an example so you can see that. But basically the same sort of redox process occurs that we are thinking about. With the oxidation reaction, it's going to still be donating those electrons. In the most case, it depends again, like the specific examples, but the general pattern is that when I'm talking about my oxidation reaction, I would have my cation becoming the metal. So basically, sorry, have it the other way around. Metal becoming the cation, because if we think about a metal, say for example, like iron would lose its electrons to become iron 2, for example. So in this case, what would I see happening in this in this beaker is that my metal would be becoming the ions. And since it's becoming the ions, we would see this electrode degrade. So we would commonly see as the pattern that the anode would be losing mass. Now it's going to obviously be donating its electrons. And we're going to have the reduction on the other half. So with that reduction happening on the other half, basically I would have the opposite reaction. I would see that my cation is becoming the metal. So for example, I would see that the copper 2 ions would be gaining the electrons to become the copper metal. I'm just going to plop in some electrons so you guys can see what I'm saying when I say oxidation and reduction. So since I am then reducing it to form the metal, I would expect my ions to go towards the electrode, and my electrode would become larger. So I would say as an observation that this electrode would gain mass as a general principle. Again, it really depends on what the reaction is, but in most cases, what we're going to be talking about is 2 different sets of metals and their ions when we're looking at that. One more piece of the puzzle that I need to talk about, and that is going to be this salt bridge. So you have to remember that everything is a circuit, and so I need this salt bridge here to complete this circuit. So basically, if my electrons are going this way all the way around, I would expect my negative ions to be coming down here to basically finish that circuit, because we need to have some sort of mobile charged particles for that. So it doesn't need to be electrons, it could just be ions. So what this means is that the salt bridge is often something that isn't terribly reactive. Very commonly you would see potassium nitrate as what is inside the salt bridge itself, connecting everybody together. You could also see the opposite with the positive ions moving in this direction to again balance the charge, because we know that these positive ions are being reduced. I should actually include in that image the ions moving. So in this case, positive ions are going towards, whereas in the other half, the oxidation half, positive ions are being released. So I hope that makes sense when we're thinking about the overall picture. It'd probably make more sense once I go through the specific example. The other thing to keep in mind is that whenever we're using inert electrodes, these inert electrodes are being used when basically the oxidation pair, the reduction pair are both aqueous. or the metal created is very reactive. Say, for example, anything in group 17. This sort of inert electrodes, and what I mean by like the pair being both ions, you'll see that in the next lesson because I'll do some examples that are like that. I just want to keep it simple to begin with. But that's our overall kind of setup and what we're thinking about when we're looking at our galvanic cell and the general sort of design. Anyway, I think if we go back to the PowerPoint, here we go. All right, so this was the gift that I showed you guys earlier. I'm going to do this one as my example. So in this case, we have iron in an iron 2 nitrate solution and copper in a copper nitrate solution. And basically, I'll do the working for you, and I'll show you the A, M, and E requirements, so that way you know how that works. But just to supplement some more information, when we do these galvanic cells and these redox reactions, we need to take the redox couple. And so basically, the species involved in the oxidation and the species involved in the reduction process are going to be pairs together. So for example, I'm dealing with iron 2, and therefore I have an iron electrode. I'm dealing with copper 2, so therefore I have a copper electrode. We want to keep these guys paired, and you'll see when I do the drawing why that is the case. It basically has to do with the fact that I need to be able to replace ions that are lost. Or I need a source for ions to be created. I could also have a redox pair where both of those items are ions that are aqueous. And so if that's the case, I will need to use an inert electrode, such as a carbon one, and I will show you guys that in the next lesson. So let's look at this example here. Just going to pause real quick so I can pull up the marking schedule. All right, cool. So here is my example that I'm thinking about, which is in the gift as well. So we have basically the pair of iron 2 and iron and copper 2 and copper. When we give you this, I can't remember if in the statement I give you the observations. Just double checking what I have on the practice question. No, I don't give you the observations because you need to use the resource sheet to figure it out. All right, so if I was just to try to make some notes on things to try to remember it, first thing I would just make sure I always write down is that this is a spontaneous reaction. For the merit, then in this case, you would take it one step further and you would calculate out the E cell, but you don't know how to do that yet, so we're going to hold off on that. And then if I was to get myself up to the excellence, I would just be stating that this E cell is positive, so therefore it is spontaneous. But again, we will do the calculations next week because I don't want to overwhelm you. And in fact, it's really dead easy, so it won't be too much of an add-on. I just want you to focus on first the galvanic cell and how everything works. All right, so the other thing I can do from the beginning is I can label my electrodes as cathode and anode. Personally, I'm not going to do that because in most cases we will label the electrodes for you and tell you this is the copper electrode and this is the iron electrode. Otherwise, you need to figure it out. Actually, let me do that for you. Let's say I have told you which side is which. So we're going to do, just as in the diagram, that this here is the iron electrode. And this here is your copper electrode. And let's say I've also labeled the solutions below. Let's say I've said that this is iron nitrate, and it's iron 2, and this is copper nitrate. And this is both aqueous. Let's say I tell you that. So it's already labeled. All right. So my first kind of point of call in order to get an achieved is I need to be able to state the oxidation and reduction reactions, identify which one's which, and what the products are going to be. So we are going back to this resource sheet, and I am basically looking for copper and copper 2, and iron 2. So I gotta find it. Here is copper and copper 2, and then here is iron and iron 2. So from this information here, I'm looking at these two numbers, and the number that is higher, so basically the higher standard reduction potential, tells me that this is ease of reduction. So what this means is that this reaction here is going to be easier to reduce. So I am just going to quickly write on this side so that way I know. On the copper electrode side, I would see a reduction. And then when I look at the iron and iron 2, like I said, the number is lower, so that's ease of oxidation. So this means that this iron electrode will have the oxidation reaction. So I'm already starting to get myself there. The other thing I will need to then do is basically give myself, or give me, the definitions of reduction and oxidation. So this is reduction. So in this reduction reaction, I will see a gain of electrons, or you could write down that you know that the oxidation number is going to decrease. For the oxidation reaction, you know that you're going to lose electrons, or you could write down that you know that the oxidation number is going to increase. So again, just really general definitions is what I'm looking for. So that's the other component for the achieved. The last component for the achieved is just stating what you know is going to happen in a sense of that redox reaction. So I have stated that the copper electrode is going to be the reduction. If I look at this reaction here, we have to remember that this pair is in the direction of reduction and the opposite is in oxidation. So since I have stated the copper is the, or copper to copper is the reduction reaction, I would then be stating that I would know that the copper 2 will be reduced to copper. On the flip side then, I have the iron 2 and the iron, and now remember I need to write this in reverse because I'm talking about the oxidation and this direction is the reduction. So I would say that the iron will be oxidized to iron 2. That's basically where most people will trip up, is that they'll just pull the wrong information. They often just get it flipped the wrong way around. So use that standard reduction potential, and from that you can then figure out oxidation and reduction reactions. If you go on to the merit then, what I'm looking for are my half equations, and those half equations can help give me specifics in that justification. So for example, I would be writing out for my reduction reaction, copper 2 plus the 2 electrons becomes the copper metal, and that verifies what I have stated here and what I've also observed. Tying in specifics, it's gained 2 electrons, the oxidation number has decreased by 2. Specifically, I see it going from positive 2 to 0. On the flip side, I would have iron becoming iron 2 plus, losing those 2 electrons. That verifies that I am looking at the oxidation reaction. I do have these guys pulled correctly. So in this case, loses 2 electrons, oxidation number has increased by 2. Oxidation number has gone from 0 to positive 2. So that's one thing that we are looking at for the merit. So like I said, achieved stuff, all in red, already done. I have passed. Now I'm just trying to get my merit. The other thing you will need to do for the merit is you will need to state your observations. There are 4 separate observations you can make. Basically, 3 out of 4 of your observations is going to be your merit point. And then if you get 4 out of 4 observations, you get your excellence point. So let me show you what I mean by observations. So first off, make sure you're commenting on the electrodes and what's happening to them. So I will notice in this case, because the iron is going to iron 2, I would make the observation that the iron electrode will decrease in mass. It will get smaller. I would see that this would degrade, so you can draw it as a little degradation. When it comes to the copper electrode, I would be stating that the copper electrode will increase in mass. We can annotate this by just kind of showing that my electrode's getting bigger. So those are observations with the electrode. The other observations I would be making would be the solutions. So here's 1, here's 2. In this case, we have more iron 2 being formed because as I think about this oxidation process, I'm creating more iron 2 ions. So I would observe in the solution in this beaker will become greener because we have an increase in the iron 2 ions. So that's my observation number 3. And then I'm doing observation 4 in the green because you need 4 out of 4 for the excellence. So in this case, my solution will become less blue. And that's because we see a decrease in the copper 2 plus ions. And that's because it's getting reduced. You can write due to its reduction if you want to be fancy. Remember, you can use shorthand, you can just annotate. I don't need a whole lot to kind of prove your understanding. But basically, we're trying to understand what's going on. So I can also draw Cu2 plus is going over there. Cool. Last thing you would then need to do for the excellence is include that full equation. So in this case, I see the electrons are on opposite sides. One is on the product side, one's on the reactant side. I can see they're already balanced and canceled out. So I don't need to do anything. I just need to write the full equation. So I'm just going iron plus Cu2 plus is becoming iron 2 plus Cu. And that's basically it. I'm just trying to double check. Yeah, so the only thing that would be kind of missing is just that E cell calculation. Cool. All right. Other things that you can note, I'm just going to put that in purple. Just like I said, these things aren't required, but it just shows me that you understand what's going on. You can show your electron movement. That tells me you know what's going on because you know that this is the oxidation reaction and that's the reduction reaction. You can tell me that you know that, oh, you actually should have written it down. Oh no, you don't. You're not required to write it down for the galvanic cell, but you would note that this is your cathode. Now remember that the cathode is swapped. In this case, it's going to be positive. You can write that this is the anode, and that is negative. You could also write down that you know how the ions are moving. So in this case, we have the negative ions moving in that direction to complete the circuit. You have your positive ions moving down there to replace the positive ions that are being lost when that copper gets reduced. But that's the whole shebang. So as you can tell, you can see what I'm saying. The galvanic cell is a little bit more complicated than the electrolytic, simply because you do have those 2 beakers and you do have to kind of think about the standard cell potential. Also be mindful, these observations I've just grabbed from looking at this table here. So I can tell iron 2 is green. I can tell that the copper 2 ion is blue. I could also note when I'm looking at it that when the mass is increasing, it's getting more of that brown or pink metal. So all of that comes through and helps. Looking at my marking schedule, actually, I have a feeling that this specification isn't actually needed for the merit. It's actually an excellence requirement. So let me just fix that. The thing is, though, most people either tend to get an achieved or an excellence. There tends not to be too many people that just get the merit simply because the jump is bigger going from achieved to merit than merit to excellence. Most people, the reason why they get the merit instead of the excellence is they forget one of the observations. They usually forget a lot of the solution observations. The thing you have to remember is that even if the solution doesn't change color, you need to state that it doesn't change color. So be mindful when you're dealing with things such as zinc, because zinc going to the zinc 2 ion or vice versa, you won't see a visible change in the solution, and you need to state that as an observation. No visible change. So do keep that in mind. All right, I think that then covers everything for this first lesson. I'm sorry that it is a bit long. It is kind of that first look at the galvanic cell, which is why it's going to take you a little more time to kind of process it. But here is the follow-up work for today's lesson. So you might have thought this is really hard and I don't quite get this, and so I would suggest then doing SciPad pages 58 to 59. Those are just really good to help you develop your vocabulary. So you take a little break from looking at these galvanic cells and just making sure you wrap your head around the words. If you feel like you're doing that okay, then I would suggest ESA Activity 25C. This is good because it doesn't make you do the galvanic cells. It just makes you learn how to use the standard reduction potential and basically helps you figure out which one's oxidation, which one's reductant, which one's a stronger oxidant, which one's a stronger reductant. Just real kind of foundational stuff, which is going to be useful to just classify and identify. The SOAR stuff then would be the SciPad pages 60 to 61. That one has specific questions geared towards galvanic cells. So to start wherever you want, stop wherever you feel like you're ready to stop. That is basically the work that I recommend you to do. You are not expected to do all of it because that is quite a bit of work. Just do what you feel like you need to do. All right, so that covers then lesson number 2 of this week. So as I said, basically you should be exploring how that galvanic cell works, how it produces energy, and just having an understanding of the basic sort of setup.